Your car's engine could feel perfectly smooth, yet be secretly waging a war against itself. A single contaminated sensor, often no larger than a thumb, can be the hidden saboteur causing a stealthy decline in power, a mysterious spike in fuel use, and a slow march toward premature engine failure, all without illuminating a single warning light. On your dashboard, this is precisely what makes the issue so insidious. How is it possible for one tiny part to make a vehicle feel lethargic, guzzle gasoline, and fail emissions inspections simultaneously? It's a frustratingly common scenario played out in repair shops and dealerships across the country every day. Car owners, desperate for a solution, replace perfectly good spark plugs, spend money on new ignition coils, and even swap out entire fuel pumps, only to find the problem persists. Thousands of dollars are spent chasing ghosts in the machine, all because the true villain is a sensor that mechanics and enthusiasts alike rarely think to clean. And no, it's not the one you're probably thinking of. There is a covert operative that spends years accumulating a film of grime, feeding deceptive data to your car's engine control unit ECU, and methodically transforming a robust engine into a shadow of its former self. In this breakdown, we will dissect the most common culprits, the engine sensors that frequently fail in silence, but the one that causes the most headaches, the one that is almost never serviced, and the one whose proper cleaning can radically alter your engine's personality. In a matter of minutes, that one will be saved for last. Number 13. The mass airflow MAF sensor. Mass airflow sensor is simultaneously one of the most vital and most chronically overlooked components in any modern fuel-injected engine. Its sole purpose is to quantify, with incredible accuracy, every single gram of air being drawn into the engine cylinders. The majority of MAF sensors in American vehicles operate on a hot wire principle, employing a platinum filament finer than a human hair. This wire is heated to a precise, unwavering temperature as the rush of intake air flows over it. It has a cooling effect that is directly proportional to the volume and speed of the air. The ECU isn't measuring the air itself. It's monitoring the electrical current needed to counteract that cooling and maintain the wire's target temperature. This current draw is then instantly converted into a precise air mass figure, updated many times per second. The catastrophic problem arises when this delicate wire becomes coated with a nearly invisible film of contaminants, fine dust that bypasses the air filter, oil vapor from high-performance filters, or even pollen. This contamination insulates the wire, altering its thermal properties and corrupting the data it sends. The ECU, now operating on flawed intelligence, believes a different amount of air is entering the engine than what is actually true. In response, it injects an incorrect amount of fuel. The symptoms are often perplexing and misdiagnosed: a noticeable hesitation or lack of power under heavy throttle, a gradual decrease in fuel economy, a wandering or unstable idle, and in severe instances, the engine stalling completely when you brake to a stop. Diagnostic data reveals that almost 40% of engine trouble codes related to air-fuel mixture imbalances are caused by a dirty, not a failed, MAF sensor. Cleaning it requires a special aerosol cleaner and a strict no-touch policy with the fragile sensing element. But there's another sensor that measures air using a completely different method. Number 12. The Manifold Absolute Pressure MAP Sensor. The MAP sensor embodies a different philosophy for calculating the engine's workload. It's a cornerstone of the speed-density fuel injection systems common in many domestic vehicles. Rather than measuring the volume of air flowing, the MAP sensor measures the air pressure or vacuum within the intake manifold. It uses a tiny piezoresistive silicon chip that alters its electrical resistance as the pressure around it changes. It's a simple, robust way to translate engine load into a voltage signal. At idle, with the throttle plate closed, intake vacuum is at its highest, so the sensor reports a low absolute pressure. When you floor the accelerator, vacuum plummets, and the pressure inside the manifold rises to nearly match the outside atmospheric pressure. The ECU takes this pressure reading, combines it with data on engine RPM and air temperature, and uses a set of complex thermodynamic maps to calculate the mass of the incoming air. The most common point of failure is not the sensor itself, but the vacuum line that provides its reading. A tiny crack in a vacuum hose, a loose fitting, or a port clogged with carbon can completely skew the pressure data. The sensor now fed false information, reports a higher pressure, less vacuum than exists, fooling the ECU into thinking the engine is under a much greater load. This results in the computer commanding excessive fuel injection, leading to drastically poor fuel economy, clouds of black smoke from the tailpipe, and persistent rich mixture fault codes. In a professional shop, more than 80% of problems blamed on a faulty map sensor are resolved by simply cleaning the sensor's port and ensuring the integrity of its vacuum line. But an even more influential sensor exists when it comes to keeping emissions in check. Number 11, the oxygen O2 sensor, often called a lambda sensor. The O2 sensors installed in your exhaust are the ECU's frontline informants on combustion efficiency. They are the key to the constant, real-time adjustments that fine-tune the air-fuel ratio thousands of times every minute. Most cars use zirconia-based O2 sensors, which feature a ceramic element heated to over 600 F 300 Celsius. This element has a unique property. It generates a voltage that varies based on the oxygen differential between the hot exhaust gas and the clean outside air. When your engine is running at the chemically ideal stoichiometric ratio of 14.7 to 1, the sensor produces a baseline voltage of about 0.45 volts. If the fuel mixture turns lean, too much air, the oxygen content in the exhaust rises, and the sensor's voltage drops. If the mixture goes rich, too much fuel, the voltage climbs. The primary issue is that these sensors are susceptible to being poisoned. Deposits of lead, silicone from certain sealants, or phosphorus from burning oil can coat the active zirconia element. This contamination doesn't cause an immediate failure, but instead makes the sensor lazy and slow to respond. It still generates a signal, but it's a sluggish, delayed one that the ECU can't use effectively. The engine ends up oscillating between rich and lean states, leading to increased fuel consumption, a noticeable lack of power, and a near-certain failure on an emissions test. However, a different kind of position sensor can fail and create an entirely separate and equally frustrating set of problems, and this is where the mystery deepens. Number 10. The throttle position sensor TPS mounted directly to the throttle body. The TPS is a simple yet crucial potentiometer that acts as a direct line of communication between your right foot and the engine's brain. Its job is to report the precise angle of the throttle plate at all times. Internally, it consists of a strip of resistive material and a wiper arm that moves across it. As the throttle opens and closes, this movement acts as a voltage divider, sending a signal to the ECU that typically ranges from about 0.5 volts at closed throttle to 4.5 volts at wide-open throttle. The ECU uses this information to make critical decisions. Is the driver feathering the gas, prioritizing fuel economy, or are they demanding maximum power, requiring a richer fuel mix and more aggressive ignition timing? The real trouble starts as the resistive track inside the sensor wears down over tens of thousands of movements, creating dead spots. These are tiny areas where the electrical contact is momentarily lost, causing the voltage signal to drop out or become erratic. These dead spots almost invariably form at the most frequently used throttle positions, the slight opening for highway cruising or the position used for idling in traffic. For the driver, this manifests as a sudden jerk or hesitation during acceleration, a brief loss of power at a specific pedal position, or even the engine stalling as the throttle moves through a worn-out section. A technician can diagnose this by monitoring the TPS voltage on a skin tool while slowly opening the throttle, looking for the telltale voltage drops that confirm internal wear. Number 9. The crankshaft position sensor. Without a functioning crankshaft position sensor, a modern engine is effectively flying blind. This small but mighty sensor is mounted near a toothed wheel on the crankshaft, and its job is to generate a precise electrical pulse every time a tooth passes its magnetic tip. What's really happening is the ECU is using this stream of pulses as its master clock. It's how the computer knows the exact rotational speed of the engine and the precise position of every piston in its stroke. This data is the absolute foundation for ignition timing and fuel injection. Without it, the engine cannot run. When the magnetic tip of this sensor becomes coated with a paste of metallic shavings, baked on oil, and road grime, its ability to read the passing teeth is compromised. The signal becomes weak, distorted, or intermittent. Symptoms can be maddeningly inconsistent. The engine might suddenly die when it gets hot, and then restart after cooling down. It might take longer than usual to crank and start, or it might experience momentary losses of power while driving. It is a common sight in repair shops to see an engine with what appears to be a major ignition failure completely cured by simply cleaning the crankshaft sensor's tip with a rag and some contact cleaner. But knowing where the crank is isn't enough. The ECU also needs to know what the top half of the engine is doing. Number 8. The camshaft position sensor (CMP). The camshaft and crankshaft position sensors operate like a perfectly synchronized duo. While the crank sensor provides the orchestra's rhythm, the overall engine speed and piston position, the cam sensor provides the soloist's timing, identifying the specific phase of each cylinder's 4-stroke cycle. This is the data that enables advanced features like sequential fuel injection, injecting fuel only for the cylinder that's on its intake stroke, and variable valve timing. The sensor is typically located on the cylinder head or timing cover, reading a notched wheel or a single peg on the camshaft. Its critical task is to send a unique signal once per camshaft revolution, which tells the ECU cylinder number 1 is now beginning its power stroke. When this sensor gets caked in oil sludge, or if internal components begin to fail, the ECU loses this crucial reference point. It doesn't shut the engine down, but instead reverts to a limp mode. It abandons precise sequential injection for a less efficient batch fire mode, where injectors are fired in groups. The result is a noticeably rougher idle, difficulty starting the engine when cold, and a strange hesitation that often appears between 2,000 and 3,000 RPM. This hesitation is frequently misdiagnosed as a bad coil or a clogged injector, when the real cause is a contaminated chem sensor sending a weak signal. Number 7. The intake air temperature (IAT) sensor tucked away in the intake manifold or air duct. The IAT sensor is so small and unobtrusive that most people are unaware of its existence. Its function seems simple: to measure the temperature of the air entering the engine. But the implications of this measurement are critical for optimal performance and efficiency. Cold air is denser than hot air, meaning it contains more oxygen molecules in the same volume. The ECU relies on the IAT sensor's data to make fine adjustments to the fuel mixture, adding a little more fuel when the air is cold and dense, and a little less when it's hot and thin. Over time, this tiny thermistor becomes coated with a sticky film of oil vapor and dust. Once insulated by this layer of grime, it can no longer accurately gauge the temperature of the passing air. It might report that the air is hotter or colder than it actually is. This forces the ECU to operate with a slight but constant miscalculation, causing the engine to run perpetually rich or lean. The effects are subtle but real: a gradual loss of power, a slow decline in fuel economy, and in some hot climates, an increased risk of engine knock detonation. A careful cleaning with a dedicated electronic cleaner is often all it takes to restore the sensor's accuracy and stabilize the air-fuel ratio. But another temperature sensor watches over something far more critical: the engine's own core temperature. Number 6. The engine coolant temperature (ECT) sensor. The CT sensor is arguably one of the most influential inputs the ECU receives. It's rarely the first suspect in a drivability problem, yet it informs a vast array of the computer's decisions. This sensor tells the ECU the precise temperature of the engine block itself. Based on this single reading, the ECU manages the cold start fuel enrichment, adjusts the idle speed, modifies ignition timing, and controls the cooling fans. When you start a cold engine, the ECU commands a rich mixture and a high idle based on the ECT's reading, then gradually tapers those settings as the sensor reports the engine is warming up. When the sensor's probe becomes coated with internal corrosion, scale, or sludge from neglected coolant, its readings become inaccurate. It might tell the ECU the engine is still cold long after it has reached operating temperature, or vice versa. This leads to a host of problems: persistently high fuel consumption because the ECU thinks it's always in warm-up mode, or rough, idle, hard starting, cooling fans that run constantly or not at all, and accelerated long-term engine wear due to the improper fuel mixture. Countless engines with seemingly complex issues have been restored to perfect running order simply by replacing a faulty ECT sensor. And yet, there remains a sensor that almost no one ever cleans. One that is responsible for some of the most expensive and misunderstood problems of all. Number 5. The Vehicle Speed Sensor VSS. When your speedometer starts to behave erratically, your automatic transmission begins to shift at strange times, or your cruise control deactivates for no reason, the silent offender is very often the vehicle speed sensor, usually mounted on the transmission or differential. The VSS generates a series of electrical pulses that correspond directly to the rotational speed of the drive shaft or wheels. What's really happening is that the ECU is translating this pulse train into a clear data point, the vehicle's road speed. This information is used to command transmission shifts, manage fuel cutoff during deceleration, and operate systems like ABS and cruise control. When the sensor's magnetic tip becomes caked with a mixture of gear oil, road dirt, and fine metallic particles, its signal becomes unreliable. The pulses may be weak, intermittent, or misshapen. The ECU might think the vehicle is moving faster or slower than it is, or even that it has stopped while it is still moving. In a diagnostic setting, mechanics often find that a thorough cleaning of the VSS, removing the metallic fuzz stuck to its tip, and flushing its electrical connector can completely resolve erratic shifting behavior that a driver might mistake for a catastrophic transmission failure. But there is an even more critical sensor, one that listens to the heart of the engine like a doctor's stethoscope. Number 4. The knock sensor bolted directly to the engine block. The knock sensor is essentially a highly tuned microphone designed to listen for one specific sound: the high-frequency ping of engine knock, also known as detonation. This is the sound of abnormal combustion, a destructive event that can damage pistons and bearings. What's really happening is this piezoelectric sensor converts the engine's mechanical vibrations into an electrical signal. The ECU continuously analyzes this signal, filtering out normal engine noise and listening for the unique signature of knock. When it detects the onset of detonation, perhaps due to low-quality fuel or extreme heat, it reacts in milliseconds, retarding the ignition timing to protect the engine from damage. The problem is that if the sensor is covered in grime, if its mounting bolt is loose, or if it was over-tightened during installation, its sensitivity is dramatically reduced. It can no longer hear the subtle vibrations it's designed to detect. This creates dangerous scenarios. In one, real detonation goes unheard, and the engine continues to operate in a self-destructive state. In the other, the sensor might pick up other vibrations and send false signals, causing the ECU to constantly pull back ignition timing, robbing the engine of power and making it feel sluggish and unresponsive. Simply cleaning the mounting surface and reinstalling the sensor to its correct torque specification can awaken a tired-feeling engine, but some sensors don't protect the engine. They only warn you when it's on the brink of disaster. Number 3. The oil pressure sensor. The glowing red oil can on the dashboard is one of the most terrifying warnings a driver can see. Behind that light is a simple pressure switch or sensor, a component that gets no attention until it's potentially too late, threaded into a main oil gallery in the engine. Its job is to detect when the system's oil pressure falls below a critical safety threshold. In its simplest form, a diaphragm inside the sensor moves under pressure, completing or breaking an electrical circuit. More advanced sensors provide a variable signal for a gauge over thousands of miles. The tiny orifice leading to the sensor can become clogged with oil sludge, varnish, or carbon debris. This restriction acts like a dam, preventing the true oil pressure from reaching the sensing element. This can lead to the sensor reporting normal pressure even when the engine is being starved of oil. The opposite can also occur, with a clogged sensor responding slowly and triggering false low-pressure warnings. Repair shops have documented countless cases where a dashboard gauge showed healthy pressure while a mechanical gauge connected directly to the engine revealed a dangerously low level. This is why cleaning or proactively replacing this cheap sensor during major service intervals is a vital, though often overlooked, preventative measure. But there's another gauge that lies to us even more frequently. Number 2, the fuel level. Sensored fuel gauge seems like a minor convenience until your car sputters to a halt on the interstate while the needle still points to a quarter tank. The culprit is the fuel level sending unit, a sensor that spends its entire life submerged in gasoline and is almost never serviced. The system is typically a simple float attached to an arm that wipes across a variable resistor. As the fuel level changes, the float moves, changing the resistance and, consequently, the reading on your dash. What's really happening over the years is that the resistive strip becomes oxidized or coated with varnish deposits from fuel additives. This creates dead spots or areas of high resistance. The result is a gauge that jumps around erratically, gets stuck in one position for days, or takes forever to update after you fill the tank. While it seems like a minor annoyance, many driver complaints about terrible gas mileage have their roots in a fuel gauge that is simply lying about how much fuel is actually being used. Number 1, sensor connectors and wiring harnesses. A surprising number of complex diagnostic cases. Hundreds or even thousands of dollars are spent replacing sensors that are, in fact, perfectly fine. The true failure lies not in the component, but in the electrical pathway that serves it, the connectors and the wiring harness. Every single sensor we've discussed is utterly dependent on a trifecta of electrical integrity: a stable power source, a solid ground connection, and an unobstructed signal path back to the ECU. What's really happening in millions of aging vehicles is a slow, relentless process of degradation. Engine vibration, moisture, and extreme heat cycles take their toll on plastic connectors, metal pins, and copper wire. A fine green film of corrosion grows inside a connector, creating resistance. A wire frays and makes intermittent contact. With every bump in the road, a critical ground connection becomes loose and corroded. A scan tool will report a fault code for a specific sensor, but in the hands of a skilled technician, wiggling the wiring harness will make the problem appear and disappear. This is the ghost in the machine. What most drivers never realize is that a meticulous cleaning of electrical connectors, the repair of a faulty ground point, or the proper securing of a harness can permanently solve problems that seem to point to a major component failure. That is why the most experienced technicians live by one rule: always inspect the wiring before condemning the sensor, because more often than not, the problem isn't with the messenger, but with the path the message travels.